Ladies and gentlemen, let me introduce to you a new distributed data storage technology that will revolutionize and liberate a world as we know it. A system designed to make content moderation and censorship obsolete. A system where copyright infringement is impossible to track and prove. Imagine a distributed data storage that is not just decentralized, but also inherently resistant to control by governments and law enforcement. The content in this data storage is not static nor dynamic, it is something in between. It is evolving content that allows users to share ideas, photos, videos, and other files of any kind with the broad public while preserving the anonymity of the author. Unlike other technologies, the data cannot be controlled or suppressed by governments. This is all possible because of new crypto stuff you have never heard of, but I'm about to explain it in a few moments in a greater detail. But first we need to talk about the historical approach and a few historical applications. Those are all these bad goodies. These technologies were created long ago in the 90s and early 2000s when hardware and software was not as advanced as it is today. They may seem like dinosaurs compared to what we are about to create. For example, RapidShare. Once popular in the early days of the internet, had several significant disadvantages. For example, limited accessibility was a major issue. If you remember, only paying users enjoyed the full-speed downloads, while others faced restrictions like slow speeds or mandatory waiting periods. Additionally, it was a centralized client-server architecture, in the end easily taken down by law enforcement. Napster, on the other hand, used a peer-to-peer file sharing, but its centralized database remained susceptible to the same issues as RapidShare. GNU-Tela, Torrent, and IPFS partially solved the problem because the technologies are truly decentralized, including their main registries. But the major problem was not tackled at all. They are struggling with copyright infringement issues, and there is no protection against infiltration attack, which is a method widely used by law enforcement and copyright holders/protectors, where those so-called legal agents join the network and pose as regular users. They then monitor the activity in the network and gather evidence of illegal file sharing. In the end, they will attack the network by issuing fines and eventually putting suspects into custody. At this moment you would think, well, paid VPN is going to save me, but please do not let me start with this topic. It is not a big secret that the most VPN providers cooperate with governments and secret agencies, and when using their services, you can be sure that every step you make is closely monitored. Well, there is an easy test which you can perform if you are not afraid. Just try to upload one or two, let's call them explicit movies featuring underage boys and girls, and then you can be sure that police will knock on your doors before midnight. There is simply just so much that the VPN providers will tolerate, so please rather do not use paid VPN at all. Finally, there is a mighty Tor. To be honest, I like Tor. Even if it is well known that over 60% of nodes in the Tor network are operated by NSA, FBI, Russians, and Chinese, I still like Tor. I have run the exit node a few years ago for almost a month and nothing special happened to me. Well, my public IP address was blacklisted and I could not reach many standard websites afterwards, but other than that, nothing special happened, except of course my 50 terabyte data package which I was supposed to use during the entire year was depleted in under 1 month. That shocked me at the time, and it is a big problem of Tor. Not only state secret agencies operate 2 of 3 nodes in the network, but Tor is painfully inefficient and slow. It relies mostly on altruists willing to sacrifice their network bandwidth and the reputation of their public IP addresses. If you look at this chart downloaded directly from Tor web pages and you zoom in on the advertised, not consumed but advertised bandwidth, you realize this thing is kind of a joke. Tor was not designed to handle zettabytes of data transfers. Frankly speaking, technologies using onion or garlic routing will never be good for content sharing applications. Which leaves us with a question. Isn't there something better? Some technology which works like a torrent for big files and as a social network for small comments and group chats, but at the same time it preserves privacy and protects users against corrupt governments. So, is there a platform which allows users to speak freely, anonymously, and to share whatever they wish, no matter if it is copyright protected? And when speaking about users, I don't mean just you and me, but I'm talking about all privacy-concerned users. Well, so isn't there something better? And the answer is yes, there is. There is a new technology which I have specially crafted for this purpose. It relies on something I call restricted multidimensional bit chains. So let me be your guide and we will rediscover this invention together. I will try to explain it step by step in a simple way so everybody will understand. First, let's define a copyrighted content. Copyrighted content can be anything: movie, music, some application, for example video games, etc. From now on, we will depict copyrighted content as this picture, or this one. On the other hand, we will use a picture of Lena as our representation of innocence, which is kind of ironic if you consider the origin of this photo. Nevertheless, Lena will represent an innocent, free, redistributable content, for example, a Linux distribution, or one of Shakespeare's poems, which can be shared and copied without a need to pay royalties. Or perhaps the best way how to define the innocence is by using our own content. This one is perfect. The Declaration of the Freedom of Speech and Freedom of File Sharing. And we can create a file of any size filled with it, 1 megabyte or 1 gigabyte or 10 gigabytes, who knows, simply by repeating this paragraph again and again. So this is what we will call an innocent document. Now imagine the following setup. We have an original copyrighted content and we will create a random binary noise of the same size as the original file. Then we will apply an exclusive OR operation between the original file and the noise one. Just a quick reminder, what is an exclusive OR operation? It is a binary operation which is extremely quick and simple. The definition is as follows. 1 XOR 1 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, 0 XOR 0 is 0. And we are going to apply the exclusive OR operation bit by bit between the original file and the noise 1, resulting in a noise 2. If you think about it, we can later use the exclusive OR operation between noise 1 and noise 2 to retrieve the original copyrighted content. But that is not our intention at the moment because there needs to be one more step to make it legal. Now imagine that we will take noise 1 and noise 2 and XOR both of them with the innocent file, resulting in the creation of noise 3 and noise 4. Now let's save and publish such files from at least 2 computers in different countries, and they will be shared by different people which have nothing in common. They do not know each other. One is in Australia and the other one in Denmark. If we use this approach, it will be very hard, almost impossible, to convict Billy from Australia that he is doing anything wrong, and the same applies to Carl in Denmark. Such a scenario is good, but there are 2 major problems. There is a small big problem with the size of the file. Let's assume that in our example the original copyrighted content is a movie with a size around 1 gigabyte. That means that we would need to create and share 4 gigabytes of noisy data. If that was the only price to pay, so be it. The internet connection improved significantly during last decade, but it is definitely not nice, we can agree on that. Unfortunately, there is another big problem. How on earth are we going to distinguish a noisy file from a copyrighted content? Imagine that somebody asks you to openly share a file and they claim the file is just a noise which is free and redistributable. How on earth are you going to verify that statement? The file, which looks like a random ones and zeros, could very much be a list of sensitive data in unknown format, or copyrighted movie compressed using a new codec, which you are not aware of. Sharing such a file can cause you some serious troubles, if even there was an algorithm which can solve both issues at once. the file size problem, and the identity problem. Such algorithm would allow us to create distributed data storage where anybody will be able to share anything and say anything with no legal consequences. Of course, there is no such algorithm. At least I thought so, until I've discovered it. So stick with me, guys, because this is gonna be a ride. First, we need to identify where is the problem. Everybody splits files vertically. We need to slice them horizontally across a bit stream, and we need to do it in a very special way in which we will produce, for example, 4 fragments, where each bit of each fragment contains 25% of information of every bit from the original file. Here, as you can see, we are splitting the original file of size 1 GB into 4 fragments of sizes 250 MB each. But the amazing thing is that we can inflate those 250 MB fragments into 1 GB files later and XOR them together, producing the original file again. And not only that, but the binary fission operation is also ambiguous, meaning that every time we apply binary fission, it will produce a completely differently looking set of fragments. Now you may think, well, this is nonsense. How on earth are we going to slice 1 bit of information into 4 pieces? There is no such thing like a 1/4 of a bit, because information stored in 1 bit is either 0 or 1, true or false. It is indivisible. But that assumption is obviously wrong. I'm going to walk you through the binary fission process step by step right now. We can describe it as a card game. Imagine a deck of cards in which there are cards of 4 different types. We have singles, pairs, tuples or triplets, and extras. Each card has a name and there are some numbers written on them in brackets. We have 2 special extra cards here. Joker, denoted as J, which we are certainly never going to use, and null card, which you simply don't want to touch, because if you draw the null card, it means you have lost the game. And here are the rules of the game. Imagine a binary casino. As soon as you enter the casino, you realize there are tables of different colors lined up in columns. A croupier will invite you and ask you to pick a color. Let's say you will select the blue one. Croupier will then initialize the counters on a big screen in front of tables, and he will ask you to select a random number from 0 to 255. Let's say you have selected 72. He will write down your name as a player blue 72 and he will walk you to the first table. You can right away see there are these cards placed on the table: O, P, Q, and R. The croupier is going to take the first move and he pseudo-randomly selects card Q. Since there is nothing for you to choose on the card, there is only one number, the number 2. The round is already over. The croupier will write Q2 into the logbook and at the same time he will update the counters on a big screen. Because you were forced to select number 2, which means you want to protect this counter, he will add 3 to the counter 2 and he will subtract 1 from counters 0, 1 and 3. So the total sum of all counters doesn't change. After that, he will walk you to the second table. There he selects the card capital U like Utah. Now the situation is different, because there are 3 numbers written on that card, but you can select only one of them. Let's suppose that you have selected number 3. Croupier writes down the outcome of the second round, he puts U3 into the logbook, then he updates counters by decreasing counters number 0, 1 and 2, and by increasing counter number 3. And he walks you to the last blue table. There he selects card D, you select number 2, he writes D2 into the logbook, and then he updates the counters. Since this is the last table, we can start another loop by moving back to the first table. The croupier selects card O. You have no other option but to select number 0, so the round's result is O0. After that, the system updates the counters as usual. Afterwards, you proceed to the second table. Croupier selects card V. you choose number 0, and so on and so on. The game may continue as long as you will keep all counters floating above 0, but unfortunately, as soon as one of those counters reaches 0, you will lose the game. The same applies if the croupier selects the null card. Fortunately for us, we do not have a null card on any table, but for a moment imagine there are null cards. If the croupier pseudo-randomly selects the null card, then the game is lost. At this moment, you may argue that this is unfair. Nobody can control this thing. You are going to lose after a few moves anyway, but that is not accurate. There is one magical trick you can pull out and nobody is aware you can do it. You can move back through the time, for example 2, 3, 5 rounds to the past, and change your selections there. By doing so, it will affect the present time. Most likely, it will change what is happening right now. And if not, you can rewind time back even more and play the game like this 1,000 times until you get the outcome you want. Isn't that amazing? But there is much more to it. Let's say that you have played the game for several millions of rounds. Nobody understands how it's possible you have survived for that long, but everybody is happy that you are leaving. As a winning prize, you will get the transcript of a gameplay, and here is the code table showing how you can easily transform the transcript into a binary stream. For Q2, there is no need to write anything. For U3, we need to write 1 and 1. For D2, we need to write just binary 0. In case of O0, there is no need to write anything, and the V0 is written as 2 binary zeros. Of course, in case of a transcript containing millions or billions of rounds, we can find a better compression setup for tuples, because as you can see, S0, T1, U2, and V3 are compressed as a 1-bit and other tuples as 2-bit values. But it can happen that S3 is by far the most used selection in the gameplay, and it would be wise to encode S3 as 1-bit value. For that, we have an extra byte called TCS, Tuple Compression Setup. The TCS ensures that the compression of tuples is optimal. Here we have it in a diagram, the entire game's mechanics shown in one simple picture. The process of binary fission relies on this repeating procedure. First, we choose some starting text, which in our case is a declaration of freedom of speech and freedom of data sharing. Then we add the name of the player as a postfix, for example, Blue72. All of this is written into the header of the output file and we can start the game. Before the very first round begins, we initialize the hashing algorithm, which effectively acts as a croupier and converts the entire text into one big number. Let's say, in this case, the number computed by the hash algorithm is 180,230,146. We then divide the number by the number of cards on the table and compute the remainder after the division. 180,230,146 modulo 4 is 2. Therefore, the card with an index 2 is selected and we can choose a number on it. Once the number is chosen, it is written to the game log and as well to the binary output. After that, the hash is updated, the next number pops out, and we go round and round like this for as many times as we want to. Once the last round is finished, we will close the output file. Unfortunately, it often happens that the last bit is somewhere in the middle of a byte, so we fill in the remaining bits with zeros and finally write TCS byte and total count of rounds. The main thing is that the resulting binary file can then be converted back into the game log, and anybody can easily verify that the game was played properly. If we try to run this check on a regular file, for example some video in MP4 format or text file, the verification algorithm will fail almost immediately. Either the counters will reach 0 or null card will pop up. There is no chance that anybody will be able to create a meaningful file larger than 8 bytes, which can pass this test without knowing the rules of the game. And since the game starts with the declaration of freedom of speech and explicit statement saying that the file is free and redistributable, And because we know that every bit of this file reflects this initial declaration, we can be sure the file is free and redistributable. At this moment you may ask, well, what is it good for? The content of this file is a completely random mishmash of ones and zeros. Now, that is true, but we can precisely tell that this is a free and redistributable mishmash of ones and zeros. And that is the key to create the data storage into which everybody can save anything without legal consequences. Let me show you how. First step in the multi-dimensionalization procedure is to take the original file, it can be copyrighted content or just a regular file, and to transform its binary stream into the sequence of 2-bit numbers. The XOR operation for 2-bit numbers plays a key role here. For example, 2 XOR 1 is 3, 3 XOR 2 is 1, etc. So we take the original file represented by the sequence of 2-bit numbers, up here. Next, let's have this setup of a binary casino. Sometimes I will refer to it as a Fission Core or just a core. And as you can see, this binary casino contains 3 dimensions represented here by the 3 colors, red, green, and blue. Since we have 3 dimensions, it means the original file will be split into 3 fragments. First, we initialize the counters for each dimension, and then we allow 3 players to enter the casino and let each of them choose a number from 0 to 255. After that, we write the name of the players and numbers they choose in a hexadecimal format. This completes the initial setup and we are ready to go. We will take the first 2-bit number from the original file, and the croupier will select the very first card for each player on the tables in the first row. On the red table it is card V, on the green table it is D, and on the blue table it is R. And now crazy thing happens. All 3 players start talking one to each other, trying to solve a simple yet sometimes tricky math problem. They will try to find a set of numbers on their cards which, when combined by the XOR operation, will produce the 2-bit number from the original file. In addition, they should consider the current state of their counters to avoid reaching 0. So how do they do that? Well, the solution is straightforward. Before the game starts, they will create a lookup table, basically a handbook containing all the combinations of all cards that can be drawn on each row of the tables, and for each combination they compute a solution telling which numbers on those cards should be selected to successfully fission any input 2-bit number. In our case, only one option is available for combination of cards V, D, R, and the value 0 from the original file. On the V card we must select number 2, on the C card the number 1, because 2 XOR 1 is 3, and on the R card the number 3 is the only option, because 3 XOR 3 is 0. That's it, we can write down the outcome of the very first round, update counters and move on to the next table. You should also notice that some combinations of cards allow players to split a number from the original file in multiple ways. In such case, players literally roll a dice and randomly choose one option. On the other hand, there are also cases where the selected combination of cards does not have any solution. If that happens, players must rewind the time, go 1 or more rounds back to the past and try another approach. This is well illustrated in the following video, where the original file is split into 3 dimensions. I would rather stop the video right now and explain what is going on here. On the left, in this column, there are the 2-bit numbers from the original file. You can see the individual bits nicely lined up here. Then we have all 3 dimensions, all 3 players, red, green and blue, side by side. The header contains the current state of each counter. Seed is the hexadecimal number from 0 to 255 the player has chosen before the first move. Then we have the current hash from the hash algorithm. In this case, it is the output from SHA-3 256, but I am still experimenting with others. The DIMS vector shows the individual cards the player has on a table, and the yellow card is the card selected by the croupier. The number the player has chosen is highlighted in green. Numbers or options that would also work but were not selected are highlighted in yellow. Numbers that cannot be used are highlighted using red color. In the bottom right corner, you will find rather important metrics. The collisions counts tells us how often players went back in time because one or more of them either ran out of luck and their counters fell down to 0, or the selected cards of all players did not offer a solution to properly fission a value from the original file, so they need to go back and play the game differently to outsmart the entropy. The bits count here shows how many bits of the original file were already processed, and collisions per bit indicates how many times on average players had to go back to split one bit of the original file. Generally, the golden rule is to have a collision rate between 10 and 100. One important note, please ignore the end card here. It's just a visualization anchor. It tells the rendering algorithm that the seed of all players was updated and there is a need to redraw the screen. So let me play the video again, and you can see how the original file is nicely split into 3 fragments. Sometimes the algorithm goes back, sometimes it goes forward, but eventually it will split the original file into 3 fragments. And when talking about time, you may wonder how long it takes to split 100 MB of data into 3 fragments. Well, it takes tens of seconds when using GPU. However, reversing the operation to fuse fragments together and retrieve the original file can be done without GPU in a blink of an eye. So the splitting procedure is the most time-consuming. Now you must be asking, how do we know that such a Fission Core or binary casino can split any file? And that is what the next chapter is all about. Now you must be asking, how do we know that such a Fission Core or binary casino can split any file? Or let's generalize the question. What rules do we need to follow when creating a Fission Core so we can be confident such a core will split any file? First, in every row of tables there must always be a combination of cards with which we can synthesize all 2-bit numbers. Basically, there needs to be a way to fission the numbers 0, 1, 2, and 3. Another rule we must follow is to ensure the informational balance in the core. That means we should perfectly distribute input data among the dimensions. That can be achieved by calculating the average bitrate of the table from the bitrate of each card on the table, then finding the total bitrate for each column and each row. Ideally, the bitrates of all dimensions should be equal. You can probably already guess the bitrate of each card. For singles, there is nothing to write to the output file, so the bitrate is 0. Pairs always use 1 bit, so the bitrate is 1. Tuples or triplets have bitrate 1.66 per card. Actually, that is the worst possible outcome for tuples, so the bitrate is actually much lower. And the Joker card has a bitrate of 2. This means the Fission Core we have been using until now is very well balanced in every aspect. There is a bitrate of 2.66 in all rows and all columns, with the columns being much more important. If the bitrate is inconsistent and changes row by row, it doesn't affect the performance too much. But if the bitrate is inconsistent between dimensions, it will generate fragments of different sizes, which is undesirable for our use case. Another, and I would say really fundamental rule that must be fulfilled is that the total bitrate of the entire Fission Core must always be slightly higher than its depth times 2. Essentially, the total bitrate of all tables in the Fission Core must be higher than the bitrate of the input stream. If such condition is satisfied, then we can say the core has a highly positive fission potential. This is logical because on each row we are splitting a 2-bit number and we have to have enough space to store it somewhere. For example, if we omit the dimension of a blue player, then we will be forced to store 6-bit information from the original file to 5.33 bits, which is impossible. Such a core is called a compression core, and these cores rarely work. Since the input is usually an extremely compressed file, typically video, which cannot be compressed any further, the splitting process will hit into a wall and the fission resistance will approach infinity. Finally, here is a recommendation for the counter's starting values. The starting value should not exceed the depth of a Fission Core times 4. In our case, the core depth is 3, so the largest reasonable starting value of counters should be 12. Smaller starting values are safer and more secure. But on the other hand, by decreasing the starting value, the core's fission resistance increases exponentially. These are probably the most important rules which need to be followed in accordance to construct a working fission core. Well, the construction of fission cores is kind of an art. It is almost like balancing an egg on the tip of a knife. But wait, there is more. Now let's look at a special technique of creating a choke point. A choke point is a place in the game where cards on the table or combination of cards on multiple tables make it impossible for a player to successfully fission 2-bit number. For example, if we have two tables next to each other with O, P, and A cards on one table and Q, R, and B cards on the other, then there is no chance to fission the number 0 with this setup, no matter what cards the croupier picks. It is described nicely in this XOR matrix. Choke points are located around the main diagonal, but instead of numbers this time we are performing XOR operation between cards. You may ask, why do we need choke points? Well, this technique is used to create statically or rotationally resistant fission cores. It forces users to use all dimensions simultaneously rather than only one at a time. And this is exactly what we want. For example, here we can clearly see that the user must use all 3 colors to split the file. They cannot do it with 2 and they cannot do it with only 1 color. The user must use all 3. If we dig a little deeper, then it is easy to see static resistance of red dimension directly in the first step. The very first table immediately prevents user from splitting number 2 and number 3. It yields only numbers 0 and 1. Rotational resistance is not so easy to see. We define the rotational resistance of the first degree as follows. Imagine that the tables are not placed in a column, but in a circle. If we duplicate such a circle and spin it, and if we find at least one choke point in every mutual rotation of these two circles, then we can say that the dimension has a rotational resistance of the first degree. The second degree resistance can be defined in a very similar way. We duplicate the circle twice, then verify that each mutual rotation of these 3 circles contains at least one choke point. And that's it. In the case of this 3-dimensional core, the rotational resistance of each dimension is equal to infinity. It doesn't matter how many times we duplicate and rotate the red, green, or blue dimension. We will still end up empty-handed. One color is simply not enough to split any meaningful file. With this core, containing inbuilt static resistance, we can see the choke points quite clearly. If the user wants to split the file, he must use all 3 colors. So, in principle, it is not possible to split a file by using one dimension twice or 3 times by not using other colors. For example, by ignoring blue and putting 2 greens side by side. It is impossible. And here you can see it in the video. The original file is being split, it has more collisions per bit, but in the end, it always succeeds and produces valid fragments. Well, now a quick recap. What have we achieved so far? We have together discovered the technology of restricted multidimensional bit chains where users are forced to split file horizontally across the bit stream. By doing this, they are guaranteed to receive free redistributable fragments where anybody can verify the validity of those fragments. And at the same time, if the user receives only one fragment, they do not know what is hidden in it. Most importantly, one fragment on its own does not contain any meaningful information. If the fission process is performed correctly using all colors, then the size of all resulting fragments will be the smallest possible. For example, if the user splits a 1 GB file using this 4-dimensional core, he will receive a set of 4 fragments of a total size 1.07 GB. What is absolutely most important is that user cannot transform the original file into one big fragment of only one color, let's say red one. We want to strongly disincentivize this behavior. You can clearly see it in this example. If the user behaves correctly and uses all 4 dimensions, the counters go down slowly, and in every round the splitting procedure processes 2 bits of information from the original file and spreads it among 4 dimensions. On the other hand, let's imagine a user wants to fool the system and transform all data from the original file into one big red fragment, which is exactly the thing we want to prevent. First, it is impossible to achieve it with the proper fission algorithm, so the user will need to change it by creating some linear variation of this algorithm, and even then it will not work, because when he tries to mimic the behavior of the Fission Core and transform the input sequence of 2-bit numbers directly into the output fragment, the counters will go down like crazy. There is no chance he will be able to control the entropy. The only way how to transform original data into one big fragment is to use steganographic attack. Steganographic attacks are highly suboptimal, and we will touch this topic later, but for now it is safe to say there is no better way how a user can split the original file and produce a valid set of fragments while maintaining minimal bitrate, other than using a proper Fission Core and strictly following the rules of the game. But now, we are finally reaching a milestone. It is time to open the chapter where we will discuss cores with 1 or more redundant dimensions, which can finally allow us to share a digital content, possibly a copyrighted content, without facing legal consequences. And that is what the next chapter is about. Let's examine the most intriguing category of splitting cores, the N+2 cores, which have 2 or more redundant dimensions. We can use them to split the original file very quickly if we use N+2 dimensions all at once, or we can freeze any dimension during the splitting procedure and the fission process will still work as expected, it will just take a bit more time. For illustration, consider this 4-dimensional 2+2 core which can split any file using either all 4 dimensions, 3 dimensions, or 2 dimensions of different colors, but it doesn't work if only 1 dimension is used, even if it is used several times. Okay, now let's be even more specific. Let's go through an example where we want to multi-dimensionalize and share a movie of size about 1 GB. For example, The Simpsons. First, we will cut the whole file vertically into 2 MB chunks. This is done mainly to take an advantage of today's CPUs and GPUs. This allows us to significantly speed up the splitting process by running it in parallel. We mark each 2 MB part at the beginning and at the end with a tag. Typically, this is done using our peer-to-peer network's license agreement. We then insert binary data into the data element, which usually takes up all 2 MB. The only exception is the last part of the file, which in most cases is smaller than 2 MB. For example, in the case of a video of size 893 MB, the last part is only 1 MB. But this is easily solved by inserting padding before and after the 1 MB of data. Finally, we optionally can encrypt the entire 2 MB piece using a symmetrical encryption algorithm. We use this procedure not only for copyrighted works, but for all files that we want to share within the distributed data storage. In the first step, we use an innocent file, typically an endlessly repeated declaration of freedom of speech, and we split it. We have already gone through the splitting algorithm, so there is no need to explain it again. As the result, we will get 4 fragments of different colors, which the application will store in the cache. And now we can start splitting the original, most likely copyrighted file. We randomly select 2 fragments, for example red and white. Since these fragments are in the cache and they have not been compressed yet, we can use the transcript of the game directly by forgetting about which cards were drawn and just taking the numbers that were selected on the cards and XOR them with the first part of the original file. We then split the first part of the file and store green and blue fragments to the cache. After that, the whole procedure is repeated. We randomly select another 2 fragments, perform an XOR operation on the data and the second part of the original file, split the data and cache the result. The algorithm continues like this until the whole original file is properly multidimensionalized. There is one more thing worth of mentioning. For now, we have considered the situation where there are no fragments from other users stored on a disk. However, this doesn't happen in a real world. Typically, by the time when a user wants to upload their very first file to the distributed data storage, there will be, in the cache or on the hard drive, there will be some movies, games or books downloaded from other users. In that case, the user can entangle their files not only with their very own fragments, but also with fragments produced by other users. The idea is to select one fragment from the personal cache and one fragment that comes from foreign multidimensionalized file, then perform an XOR operation on it with the part of the file we are currently processing and split it. It is highly recommended to use the 3-4-3 rule, where at 30% we entangle to our own fragments, 40% of the time we entangle with one of our own fragments and one fragment from somebody else, and 30% of the time we entangle only to someone else's fragments. Here is a helpful tip to save time, effort, and bandwidth. When entangling with fragments produced by somebody else, we should use such fragments twice or 3 times. By repeating this procedure, we can process a large number of files, creating a heap of fragments representing our own file system. This is shown here with the green background. The blue and orange backgrounds represent other file systems. Now, if you are paying attention, you might argue that splitting so many files using an N+2 core will create a lot of extra data, but that is not true. The magic of multidimensionalization is well illustrated in this image. The total size of all fragments is only a couple of percentage points, say 10% more than the aggregated size of original files. This is the price we have to pay to solve all the legal problems, including those related to copyright infringement. How is it possible? As you already know, every fragment starts with the declaration of freedom of speech and freedom of file sharing. Therefore, every fragment is by nature free and redistributable. And anybody can test this because every bit of every byte in a fragment reflects that declaration from the header of the file. On top of it, the payload of every fragment is a pure nonsense. It is a scramble of ones and zeros that means nothing. To reveal a meaningful information, the user must first decompress the data and then perform an XOR operation using fragments of the other 3 colors. But if you select a different 3 colors, for example these fragments, it will produce a completely different file. And here is the catch. The protocol says the red fragments can be shared only by computers with red IP addresses. Red IP address is the address where the hash of such IP address starts with binary numbers 00. Obviously, the green, blue, and alpha fragments are shared by computers where IP addresses start with 01, 10, and 11 respectively. And now you need to ask yourself, is user or probably many users sharing this red fragment breaking any law? The answer is no. Those guys are not doing anything wrong. They behave exactly according to Constitution, and in most democratic countries this behavior is a kind of protected free speech. Imagine yourself as a copyright laws protector or law enforcement. You are very welcome to infiltrate this distributed peer-to-peer storage and you can download whatever you wish. But since everybody is publicly sharing only fragments which are of the same color as their IP addresses, then everybody is safe. You cannot stop this behavior. Also, anyone can take any fragment, mix it with copyrighted work or other digital data and publish it. This multidimensional data storage and protocol governing correct behavior is designed in a way that it is impossible to know who created the fragment, when it was created, and what kind of information is stored in it. It can be anything. It can be a photo of my cat, it can be a Linux distribution, it can be a copyrighted movie. Nobody knows. But everybody can check that the fragment was created properly and that it doesn't contain any meaningful information on its own. To be more precise, everybody can check that the fragment contains information in the state of superposition. Our distributed data storage has two major pillars: the logic behind multidimensional files and the Zettabyte protocol. The logic behind multidimensional files ensures everybody is forced to split files into fragments using the proper setup of a Fission Core, or binary casino if you wish. Otherwise, the user will not follow the logic of the game, thus, he cannot store files to the distributed data storage. Zettabyte protocol is a set of network rules which every user should strictly follow to protect themselves and to check that nobody reveals any information which can be connected to any meaningful content. But now I'm getting a little ahead of myself. Before we describe the Zettabyte protocol, let's talk about how to make a file system descriptor and how to share it with others. Let's consider a simple file system where we have one video, a folder with a text file, and a link to a file system of somebody else. First, we create a descriptor for the video, which is a JSON file containing an array of hashes describing how to put the fragments together. Once the application produces such a descriptor, it immediately splits it into fragments, like a regular file. Because the descriptor is a regular file, so it can be stored in a distributed data storage as well. Therefore, a file descriptor is actually represented by 4 hashes. The folder descriptor is somewhat more complex. A folder can contain files, subfolders, or links to other file systems. Large files, like the Simpsons video, are represented by a reference to the file descriptor from the previous slide. Smaller files can be stored directly in the folder in base64 encoding. And foreign file system linked here as a subfolder redirects the user to a file system of somebody else. The folder descriptor has the most complex structure, but it is still relatively easy to understand. Once JSON descriptor of the folder is created, it is multidimensionalized and stored in a data storage. Finally, we have the file system descriptor. This contains the signature key, the communication key. Those are so-called golden keys. Their private part is known only to the author of the file system, and the public part is a unique identification of the file system. There is also a root folder update links and root folder tachyons, which are very useful when publishing information about new file system, and they can be used for hidden communication among users. We will talk about update links and tachyons later in this tutorial, but now let's return to the topic of signature and communication keys. I think we live in an era when usable quantum computers are literally almost here. Therefore, we should always use quantum-resistant cryptography at least for our golden keys. That is why the MLDSA and MLChem were chosen as a default encryption algorithms. Finally, as always, we split the file system descriptor and store it in the distributed data storage. And here is a diagram of all 3 objects and their relationship that makes up the file system. Now let's discuss how to upload and download fragments into our peer-to-peer network. Downloading the fragments is very easy and straightforward. Uploading is a bit more complicated because, as mentioned earlier, each user can share only fragments of a certain color, which depends on a hash of the public IP address of the user. So, if the user wants to share data with the rest of the world, they have to exchange some of their fragments which are not compatible with the color of their IP address with other users. For example, if your IP address is red, meaning the hash of your public IP address starts in binary code with 00, then you, and I mean the application responsible to store data in data storage, must go to the fragments marketplace and exchange green, blue, and white fragments with other users. The exchange can happen directly or through the Tor network. Most importantly, this exchange is not widely broadcasted. It is rather limited to a tiny circle of so-called friends, and the software makes sure that it is impossible to detect who produced the fragment and when exactly it was produced. After the fragments are exchanged, the software waits a while, typically a few minutes, and registers hashes of those fragments into a distributed hash table. Again, this can be done directly or indirectly using the Tor network. As mentioned before, downloading and resharing is fairly simple and straightforward. Anyone with a file system descriptor can download any fragment of any color from the distributed data storage and combine them together to fuse, or assemble if you wish, the file system, and after that individual files of the file system. There are three major download strategies. The most common and most paranoid strategy is the strict mode, where the user shares only what they downloaded and only fragments of the same color as their IP address. The standard mode allows automatic exchange and sharing of fragments from friendly peers. Obviously, those fragments must have a proper color. Then there is a naive mode, which allows anybody to push fragments of a specific color to the user's cache. Those will then be shared automatically. But almost nobody uses naive mode. Standard mode is the way to go. There is one more thing worth mentioning. The so-called quo-pro-quit model, which effectively eliminates the existence of parasites. Parasites are those users who do not contribute to the network. They only download files but never redistribute them. The quo-pro-quit mechanism makes sure that everybody contributes to the network. For example, if Ron wants to download data from Richard, then Richard can return a completely different fragment back to Ron and order Ron to forward the fragment to Alice, Bob, and George. Only and only then will Ron get the fragment he originally requested. Of course, this behavior is triggered in situations when there is a lot of interest in a particular data to expedite fragment distribution, and occasionally as a test of obedience. Well, now we shall perform an exercise. Let's switch aside and for a moment pretend that we are law enforcement and we want to break this network down and arrest as many people as we can. We will quickly find out that in almost all cases it is impossible, but that is a topic for the next video. First, we have a naive attack with zero chance of success. Imagine a person or company complaining and saying, I have generated a random file in the past, completely random ones and zeros. It is my work. I own it. But someone stole it from me and shared it in the distributed data storage. I order you to remove it immediately. Well, that's utterly ridiculous. We all know it is impossible. Statistically, if the guy really generated a random noise, a random ones and zeros as he claims, then in 1 or 2 dozen bits he would have gone into collision. His counters would reach 0 or he would have encountered a null card. There is simply zero chance anybody can generate a file which is over 20 bytes long and it is still a valid fragment. It's impossible, so he is lying. He must have known the rules of the game and must have generated the file according to them. Since every bit in that fragment is a reflection of the initial hash, and the initial hash is calculated from the license agreement, stating that the file is free and redistributable, then he has no copyright to that file. The second thing they can pull on us is a blind frontal attack, and you can be absolutely sure someone will try it. The attack goes like this. The law enforcement or agency protecting copyright laws for some client will try to claim that Alice from Israel, Bob from Bulgaria, Richard from Poland, and George from Tunis are all together illegally sharing the Simpsons movie. Their reasoning will be straightforward. They will point the finger at Richard and say that while using the wacky rules of our peer-to-peer network, he shares a red fragment which, when combined with George's green fragment, Bob's blue fragment, and Alice's alpha fragment, produces copyrighted content. And then they will demand Richard to stop sharing the red fragment immediately. Of course, that's silly, because Richard has done nothing wrong. First of all, he does not have to talk to the police at all. It is up to them to prove their accusation beyond any doubt. But if he wants to talk, he can tell them that the red fragment he shared is a part of a video of his cat climbing a tree. Or better yet, that it is an innocent file with a declaration of freedom of speech and he has a right to share such information under the Freedom of Expression and Free Speech Act. Since a fragment is anonymous, fully redistributable and on its own, it can mean anything. Proving the person sharing it did anything wrong is nearly impossible. Then there is a third type of legal attack, which is somehow more promising than the previous two. It is an attack against a fragment of a single color, and it is called steganographic attack. I have never seen steganographic attack succeed in a court, but let's suppose it will. Honestly, this kind of attack can be pulled against any file format on this planet, and it goes like this. Imagine that somebody generated pseudo-random noise according to the rules of the game, for example the rules of the red dimension, and he did it in a very clever way that every fifth bit of such fragment belongs to a copyrighted work. That means somebody would generate a fragment from scratch not by splitting a meaningful file using the fission procedure and logic of our binary casino, but deliberately imprinting the copyrighted work and putting it in a compressed bit stream of a red fragment as every fifth bit. Such user needs to be careful to not break the red dimension's rules. Next, he throws such a fragment into a folder and uses it in a regular file splitting procedure. Finally, he shares it, he lets it live in the network for a while, and then he complains and demands immediate removal of the fragment. Okay, we have to ask ourselves, what is the yield of such behavior? Isn't it better to behave according to the rules of our distributed data storage, thus storing more data in it, rather than trying to steganographically attack one color? Of course it is. So who would do such a thing? The answer is obvious. It's a provocateur, most likely a movie producer or lawyer protecting his rights and trying to get some attention. But there is a simple and easy solution to this. Movie producers and DMCA protecting agencies typically run a blacklist or several blacklists containing hashes of pirated files. And if they can back up their claims and prove the pirated stuff is placed just in one fragment, then we will stop sharing such a fragment in the network. Or I should rather say the application will detect it in a blacklist and stop sharing it. Have you noticed what is happening? We are basically turning the copyright law against the content producers. Pirates and other privacy-concerned users are rewarded for the correct behavior in the network. They are anonymous and they are being protected by the Constitution. On the other hand, the movie producers are the only entities who will have an incentive to steganographically attack files and upload them to the data storage, and even then nobody will care. Honestly, a steganographic attack is not a major concern. It is complex, ineffective, and very weak from a legal standpoint. Most importantly, there is a much better type of attack that is optimal and which could theoretically bring down the entire network if we are not prepared for it. It is the CCR attack, and we will discuss it in the next chapter. To understand the CCR attack, we must first understand the basics of a data surface theory. A data surface is essentially a file or a part of a file that is created by performing XOR operation on the decompressed fragments. In the case of a Fission Core of type n+2, where n is equal to 2, we will have 4 dimensions, so 4 different colors. And the smallest possible data surface we can produce by this core is made up of 2 fragments. Let's call this data surface an edge data surface. There is also a triangular data surface, a square data surface, a pentagonal data surface, and so on. Well, once we decompress and perform an exclusive OR operation, we can get one of the following type of a result. We can receive an innocent file denoted by Greek letter iota. This is a file where we know every bit and byte of the payload. Typically, this is our declaration of freedom of speech and freedom of file sharing, repeated again and again until it fills up the entire space of the file. Then there is a visible data surface or alpha surface, which is a meaningful file, typically a movie, video game, whatever. The payload of such a file is correctly tagged, which means as soon as the XOR operation is performed, the resulting file contains a recognizable tag at the beginning and at the end of the payload. Then we have an empty data surface, which is a file that does not contain any tags at the beginning and at the end. The content of such a file is a mishmash of random ones and zeros that is meaningless. And finally, a hidden data surface. This surface is very similar to an empty data surface. There are no tags at the beginning and at the end of the payload, but unfortunately, the payload is a meaningful file. One might think most times we cannot distinguish between an empty data surface and a hidden data surface, but this isn't true. Let's go through the logic of low-level sharing rules, which shields users from participating in any traceable illegal activities. First, let's examine the edge data surface. Everybody can see it is impossible to create a meaningful data surface by combining two fragments of the same color. On the other hand, it is possible to create an edge data surface composed of two fragments of different colors. Such data surfaces should not be shared and must not be used for de-entanglement. Next, we have a triangular data surface. As mentioned before, if the vertices of triangle are fragments of the same color, then the result is not a meaningful file. If fragments of two different colors are used, then this is a dangerous combination. Again, such fragments should not be shared and must not be used for entanglement. If the vertices of a triangle are fragments of three different colors, then that is quite okay, but I would avoid using such fragments in the entanglement procedure. With triangular data surfaces, we can make one interesting observation. If we know that a triangular data surface is an alpha surface, for example a movie, or an innocent data surface, then we can say with 100% certainty that all three edges of such a triangle are empty data surfaces. There is nothing hidden in them. The same rule applies to square data surfaces. If the vertices of a square data surface are of the same color, then the result is not a meaningful file. If fragments of two different colors are used, then as you may already know, this is a dangerous situation. Such fragments should not be shared and must not be used in the entanglement procedure. If the vertices of the square are of three different colors, then that is quite okay, but we should as well avoid using such fragments in the entanglement procedure. Finally, if the vertices are composed of all four colors, then it is a correct data surface whose fragments can be shared and entangled. Now, what observations can we make about square data surfaces? If we know that a square data surface is an innocent data surface or alpha surface, then all internal triangles are empty data surfaces. What can we tell about edges? If we have used three fragments where we know they were created properly, and one fragment was taken from somebody else, then we can be sure of one thing: all edge data surfaces are empty. If we have used two fragments from somebody else, most likely from two different users, then there is a theoretical non-zero chance those two fragments may contain some meaningful information and those two different users are actually one attacker. But the chance of this happening is almost zero. I'm sure you are now wondering, what is this good for? Let's switch roles again. Imagine you are a copyright protector working for a big company like Universal Pictures and you want to attack this peer-to-peer network. The problem is that unlike with traditional client-server topology or when using torrent topology with multidimensional files, you cannot identify who is sharing what. So you cannot easily accuse any user/pirate of sharing copyrighted content or illegal stuff even though you know the IP address of the user. You would need to go case by case to accuse someone and to prove he or she has done something illegal. That is very costly, time-consuming, and your chances of proving it are almost zero. But there is a catch. There is a CCR attack which can theoretically tear this distributed peer-to-peer network into pieces. So, how does it work? Let's assume you have discovered the following set of data surfaces which when assembled will produce a copyrighted work or video game or whatever, and you as a lawyer want to get rid of it. In this setup, we should as well assume each fragment is shared by exactly one computer, which if you think about it, is nonsense. In a real life, hundreds of users will host and share the same fragment. But we will pretend this is not the case. So as a lawyer of some movie producer, you cannot use robots to send DMCA complaints automatically, because people sharing all those fragments are not breaching your copyright. They are individually sharing provable, redistributable nonsense. You would need to involve law enforcement to apply knock and talk strategy, which on its own, even for small user groups, is extremely costly. So, for a brief moment, imagine police going around asking real people questions about those fragments. Let's say they will first visit the person who shares this alpha fragment. Based on your allegations, they will illegally accuse this guy of copyright infringement, and let's imagine that the guy is a naive idiot who really wants to talk to police. First of all, he has no idea if the fragment he is sharing was created during a fission procedure when somebody was stealing a copyrighted stuff, or if it is a part of Linux distribution which was used during the entanglement procedure. So the guy is honestly innocent. He is sharing a measurable nonsense and he is doing nothing wrong. But, on the other hand, he can also reply that the fragment is a part of the multidimensional file containing the Declaration of Freedom of Speech, and he is sharing it because this is intended purpose of our network. Wink wink, and there is nothing wrong with it. We are just playing funny math game like what the Bitcoin guys are doing, so the law enforcement or copyright protector must go somewhere else. Okay, this time let's try the guy sharing the red fragment. And lo and behold, the same story about innocence comes out. Now let's try this blue guy, and we are back to the same story. Whether you look left or right, whoever you approach, overwhelmingly, people don't talk to you at all, or they really don't know what is going on. And you, as a policeman, have nothing in your hands to prove otherwise. That's it. This entire concept works seamlessly until somebody discovers an edge data surface. Edge data surface changes the situation 180. This is a typical CCR attack, where CCR stands for causality chain reaction. If you think about it and ask yourself, what existed first, the blue-white-green triangle or this red-white edge? Undoubtedly, the edge data surface existed before the triangle. There is no other way it could have been done. Therefore, it's clear that the blue and green fragments are tainted. They are guilty, if you wish, and the white fragment is innocent. However, perhaps, and I emphasize, there is no case study, no court ruling, and no law on the subject whatsoever. But, perhaps, in the future a court may conclude that such fragments are indeed inherently connected to the copyrighted work and therefore sharing them infringes copyright. So the files will be blacklisted and they will no longer be shared. But what is even more disturbing, from this point you can go on applying the same logic of who is guilty and who is not again and again, which will set off a chain reaction. We could then apply the same rules to this fragment and this fragment and this fragment, etc., finding that all of them are indeed connected to some copyrighted work, and we can do it until we reach a square. The propagation stops here. A square data surface always saves the day. Now, again, it is impossible to tell who is guilty and who is not. That is the main reason why we always use N+2 cores and not N+1 cores. With N+2 core, the CCR attack will not stand a chance. If somebody pulls it off, the damage will be negligible. Users who have multidimensionalized their files in a correct way are practically untouchable. The probability that a user will take into entanglement procedure two fragments created by somebody else, and at the same time these two randomly selected foreign fragments were crafted to trigger CCR attack, is virtually zero. Even if there is such an unlucky user, the application will later detect the situation because it scans blacklists from time to time, and it will repair the corrupted data surface almost instantly. The most important thing is when using N+2 cores, there is no chance to bring the network down using CCR attack. What's more, if we can go back a little and inspect the square/edge causality problem, you can easily see one thing. If the square is created the proper way, then there is no chance anybody can take one of the square vertices and produce a valid, meaningful edge data surface. It is impossible. The only way how this attack could be pulled off is if somebody first created an edge data surface and then used its fragments to produce meaningful square data surfaces, shared those surfaces in the network, waited for a long time till enough users entangled to the poisoned fragments, and then complained. It is a lot of work for minuscule temporary damage, because the application on computers of affected users will detect the corrupted blacklisted fragments and repair the damage in no time. So even if CCR attack is the most promising one, it cannot threaten the distributed data storage.